Hi, everyone. My name is Martin. I lead product infrastructure at Snapchat. I'm joined today by Fani. He's a director at Google Cloud. Today, I'm going to come and talk to you guys about our collaborations and optimizations that actually grew Bigtable's adoption at Snapchat. And we'll go over two uh, characteristic workloads and talk a little bit about the scaling profiles and challenges that we encountered, as well as all of the goodness that actually went into solving some of the scale challenges that we have to overcome over the last several months. What is Snapchat? Uh, Snapchat is the fastest way for people to send a picture or a video to your closest 4 or 5 friends every single day. And our customer base has been growing pretty consistently quarter over quarter. And this actually shows that our general customer base is very resonating with the product mission. And as a personal anecdote, uh, I actually was able to reconnect with some of my childhood friends after installing Snapchat. So now I actually know what they look like at 6 o'clock in the morning. And a few more statistics to show the scale for Snapchat. In a lot of ways, we're actually the introduction to what is social media for the majority of the, I guess, 13 to 24-year-old in the world today. You can see that over 90% of the world's population in that segment actually uses Snapchat each month. And we are still growing. We have a social graph that is ever expanding. We have a very high volume of content that's being exchanged through our platform. So why is this important, and what do we use Bigtable for? Uh, the first workload that I wanted to kind of discuss is we've built this ML feature store, and we leverage machine learning to be able to deliver personalized content and experiences to our users every day. Now, generally, how this works is a client will wake up, it'll make a call to the backend to say, "Hey, get me the next 10 videos or next 10 pieces of news that I may be interested in." That initial query may seem lack of context, right? Because all you're getting at the end of the day is a client ID. So it goes through this process called hydration. And the hydration process basically will have to fetch features related to the user and what do we understand about the content that we're trying to personalize and recommend in order, right, down to the client. So in order for this to happen, the backend actually needs to take that request and figure out ways to kind of deliver timely and also relevant recommendations. So there are several different types of ML models that are at play in order to be able to deliver this personalized experience, including things like embedding extraction models, including sequence models, including recommendation models. They all have one thing in common, which is they have to also pull from an online feature store. So what is an ML online feature store? Um, Generally, it's a place where we actually have to store and fetch dense as well as sparse features. So dense features are typically numbers, counters, arrays, and for example, the frequency of likes on certain types of content. Sparse features are generally labels or categories or UUIDs with very high cardinality, including things like user ID or content ID. So why is this a hard problem? Depending on the type of recommendation, like volume of queries that you're getting, you may or may not pick to use this architecture, but our architecture is something that we have arrived at after a couple rounds of iteration, and this generally works for something at our scale. So essentially, we have two different types of data that's constantly getting emitted from the clients. Some of them are actually streamed. Some of it will get aggregated and get processed in batch. And they will go to either the online store or the offline store, which serves different purposes in terms of experimentation that's done by machine learning engineers. And after the features are stored in their respective places, they also then get served for different downstream use cases, including model training as well as online inference or offline batch inference. So we're going to focus today primarily on the online store use case. And uh, to scale an online store, typically we have to look at the different stages of model development and what is the online store actually being used for. And that roughly follows data collection, data transforms, model training, as well as model inference, all of which actually leverage the online store in different ways. And it's worth noting that across all the different product surfaces that we have inside Snapchat, that we have very different strategies and different optimization models and different workloads that actually requires various different scales and patterns of traffic that actually has to go and store data or fetch data out of an online store. This is particularly complicated because you can imagine that there may be very, very different modalities of interaction that needs to get combined in very different ways and with different consistency requirements and as well as different serving latency profiles. So this is where we had to make some decisions early on whether we can build our own ML feature store or leverage something that is really like readily available off the shelf. And a lot of times when you look at all the lineup of feature store capabilities that's provided by different cloud vendors today, you have to ask, why did we actually go off and buy build our own ML feature store? Often you have four questions. First is, can this work? Like this particular component that we're going to build work for some or all use cases, right, in our ML lineup. The second question is, can we negotiate our way, right, into acceptable cost performance, right? In which case, perhaps it would be better to kind of leverage something that's off the shelf. The third is, what does the roadmap look like, right? For some of the features that we need, or some of the capabilities, infrastructure capabilities that we need, does that already exist, or is that on the backlog, right? For some of these solutions that are out there. And then finally, does the math work, right? Like we care about our bottom line. So is this going to increase our cost profile, and does the cost performance, really make sense? We basically thought about all these different dimensions, and then we eventually landed on building it ourselves, just because we felt that at the time there was no viable alternatives that actually met the scale of our requirements, and we did our math. Once we reach a certain economies of scale, we were actually going to be able to extract really good cost performance and future cost savings by having something that's in house. So this is where Bigtable comes in. So Bigtable has very flexible schema, and it's really, really capable at handling the high QPS, or the throughput that we were actually exerting right on top of these clusters. So you can see that we were running about 4 million reads and about 6K writes per second. And with this, Bigtable was able to achieve sub 10 millisecond latency. Something that's special about the workloads at Snapchat is we generally follow a sinusoidal wave for traffic patterns, meaning at different times of the day, we actually send very, very different traffic peaks or troves. And the underlying infrastructure needs to be flexible enough or elastic enough to be able to handle traffic surges, right, without regressing on either error rate or latency, both of which are things that Bigtable is now able to provide for us, and at very sizable data volumes as well, right? So we're running this workload on roughly about 500 terabytes of total size for the table, and there's quite a bit of variance in terms of number of features that we're fetching for different roles. The rows that it goes into ML feature stores typically are events, right? So this can be different types of predictions or different types of observations, and the columns are essentially features that are associated with certain events. So you can tell that sometimes that we may want to play with different types of features. We may want to add. We may want to subtract, and we have to play with different like lens of features in these columns. And you can see that we vary from tens to hundreds of features, right, per row. And Bigtable schema is flexible enough to kind of handle right this large variance without sacrificing runtime latency, which is very, very big plus. The second workload that I wanted to kind of talk about today is ads delivery. So with respect to ads, you can think of one of the key things that we have to solve technically is, has the user actually seen this ad I'm about to serve them, right? To answer this question, we essentially have to remember that this user has saw or has seen this ad at this timestamp sometime in the past. Obviously, you can't look back, through all time like in the past, because that will significantly increase your look back window as well as the pressure that you put onto the underlying data store. right? So the rows here are typically ads IDs, and the columns are typically engagements, right? So one key requirement here is that we require very strong consistency, meaning once a ad impression has actually taken place, we want to make sure that that does not suffer from any kind of cache coherency issues when we go and try to fetch and see whether this particular user has seen this ad already. So we need to have a low replication delay, and we also need to make sure that like our reads and writes are somehow able to get isolated within the same cluster. And an issue that like the Bigtable team was actually able to solve for us with very targeted fixes, and it's not something that is common in other workloads. So we super appreciate the Bigtable team for coming through and helping us with this. So workload characteristics wise, you can see that this is roughly 10x the amount of writes compared to the other workload, but we're actually able to achieve a very similar latency profile, even with the much larger data volume. The one other thing that I would like to call out is that Bigtable is regionalized. It's global, right? So it's present in US, Europe, as well as Asia. And even with this, cross-region footprint, the latency that we're able to see across the different regional endpoints is still able to meet this very tight latency bound that we have established as a core product requirement. So all of which are very nice, right, for us as a customer. So let's talk a little bit about some of the optimizations that we were able to land in collaboration with the Bigtable team over the last several months. So first, Bigtable actually exposes a lot of controls, which allows very fine-grained tuning in your cluster setup. And we very much value availability, latency, cost performance. And some of this optimizations is actually very difficult to do, primarily because, as I mentioned earlier, our traffic pattern is very elastic, right? So in order to be able to handle some of the load increases, we have to be able to auto scale where possible. And on top of that, we also need to be able to guarantee a certain level of service availability up to a certain amount of SLA, and beyond which we have to be able to throttle by caller as well as by tier of the workload or the query. And we see that Bigtable is actually able to handle some of these very stringent, mission critical online workloads, right? And fail gracefully when we exceed certain quotas that we establish. Uh, on top of that, for Snapchat, we really care about our P90 latency profile. If there's any latency spikes at P90, that'll actually impact customer experience and adversely affect whether we're able to, say, deliver consistent sort of recommendations or a consistent experience for, whether we can determine whether this ad has been viewed by a user or not. So on top of that, if a thread is hogging on the critical paths for some of the query replies, we see that the cluster utilizations would also go up, right? If the underlying data store is taking longer to reply, that all translates into much larger, I guess, like utilizations or unnecessary CPUs that are being wasted. They're just kind of busy waiting for replies, right? So any type of latency reduction translates directly almost to resource savings for our compute clusters. Because that translates to the same resources being able to scale to handle more requests and more efficiencies equals better cost performance, and all of which we really really like. And so some of the latency reduction initiatives that the Bigtable team has landed, right, over the last several months, including things like auto scaling to larger nodes, right? So under load, we sometimes see that we are actually CPU or memory bound, and the Bigtable team was actually able to handle through control plane optimizations, automatically selecting larger instances to be able to handle our workload traffic shifts. And some of the other sort of efficiency improvements that we made, including separating reads from writes. That's basically what we mean by write isolation. This is important because when we have traffic that is read heavy, typically you want to make sure that the writes aren't blocking the reads. So when you run into thread contention, that's when you also increase read latency. All of which we kind of explained are not desirable, right, for our production environment, and we need to be able to kind of handle like spinning up a separate cluster just to handle some of the write heavy workloads from impacting any of the read path. So some of the other optimizations I won't go over in detail, but I'm happy to answer any questions if folks want to reach out and get any additional background stories about some of these optimizations. So our favorite new features, by the way, are data boost. So we talked a little bit about read and write separation. Data boost actually is a natively supported Bigtable feature that just launched this year that is actually able to automatically handle the read-write isolation for you. So you no longer need to actually manage two separate clusters, one for read and one for write. Uh, and it's really nice because some of our use cases actually require this level of elasticity in the traffic patterns, and it just saves our team from having to worry about maintaining multiple different clusters for different slightly different traffic patterns. The second thing that we really enjoyed seeing was request priorities. So this actually will designate higher priorities uh, for user-specified payloads. So Bigtable internally actually prioritizes requests with smaller payloads by default. So this is yet another lever to allow users or customers to explicitly state prioritization orders. So all of which are very welcome feature optimizations that we've really enjoyed, and we really looking forward to future partnership with our Bigtable team. And we really appreciate all the close partnership. By the way, the graph on the bottom half of the slide actually shows adoption patterns and overall Bigtable workload throughput over the last 2 years. So you can see a consistent increase in the amount of workloads that we have been migrating over to Bigtable. And we couldn't have done it without the stellar team that's behind Bigtable. So we really welcome and really appreciate all the close partnership, and look forward to more to come. So I'll now pass it over to Fani to talk a little bit more about some of the additional features that are coming down the line for Bigtable. Fani?
Thank you, Martin, and thank you for all those kind words. I really appreciate you mentioning that. Hi, I'm Faninder Vemaru. Thanks for everyone for joining us here. I'm Director of Engineering in GCP Databases. So Martin talked about how Snapchat uses Bigtable for both a feature store use case and an ads attribution use case. So what makes Bigtable work for both these use cases, right? So we believe it is because of the fast and flexible at scale mantra that I threw there on the slide right now, right? Fast refers to low latency and price performance. Flexible talks about how we can future-proof your changing requirements and organizational structures and still work successfully. And scale refers to one of the bread and butter items of Bigtable, and hence the big, which is it'll grow with you, be it hundreds of operations or millions of operations per second. This year, we actually celebrated the 20-year anniversary of the Bigtable journey. It's a database that really kicked off the NoSQL movement, inspiring scale-out databases like HBase, Cassandra, etc. And truly, the scale part of it is one of the Google's deepest veins of technology innovations over the years. And in those 20 years, Google has built its businesses around this capability of scale of its databases, right? Bigtable brings you that knowledge and a steady hand of experience to help your business scale in a sustainable way. Speaking about scale, Bigtable has more than 10 exabytes of data under management and serves over 7 billion PQPS. It's a vitally important product for our cloud customers and Google at the same time, and it provides an industry-leading finance SLA while also providing open source friendly HBase compatibility. It's a very versatile system. We talked a lot about it in this talk, and it enables a wide range of use cases across many industries. Let's focus on a subset of these use cases that are top of mind for a lot of folks. So let's talk about ML workloads. We should take a look at the trends of ML workloads nowadays before we can answer what is good for ML workloads, right? It takes a village nowadays to build a set of features, and you want features and models to evolve over time. Your data sizes are increasing, and you need cheap ways of scaling and writing new data and doing cleanups of your data or preparing your data, backfills, etc. And we need models to be trained and updated frequently on recent data. On top of all of that, we also need real time access for RAG patterns to seed and ground our LLM requests. Bigtable, we believe, addresses a lot of these challenges. The white column nature of it helps with changing feature sets, and authorized views that we launched recently enables multiple teams to work in parallel on different feature sets. The cheap writes and scalable writes, a hallmark of Bigtable, empower you to update your features frequently to iterate over them. And training and inference can be combined if you wish within the same store using features like data boost and request priorities. I'd like to announce a few, launches, and the important ones. We don't have time for everything. We are announcing streaming reverse ETL in private preview right now. The best way to explain this feature is that you can, with just select, few SQL statements, and with no pipeline management on your part, can materialize your data from your data warehouse, BigQuery, to Bigtable. What's more is this materialization is continuous. So when new data comes into your data warehouse, it'll automatically materialize in Bigtable for your real-time access. Imagine that you created a great feature after analyzing all your data in your data warehouse, and with the click of a button, now you can provide that feature backfilled and continuously synchronized to Bigtable for real-time use. We talked a little bit about Data Boost. Martin mentioned how he was excited about it. Bottom line is now you can query Bigtable while bypassing the provision nodes. As you can see in the diagram over there, you can query, you can use your analytical query workloads by directly accessing Bigtable's data on the files and skip the whole provision nodes, and hence not interacting and isolating yourself from user traffic. This is the kind of stuff that you see usually in analytical systems, but that's the point. Bigtable can be used for both. It's a mixed workload system. In a similar way, Martin mentioned this thing again for request priorities, so I'm not going to dwell on this much. You can run mixed workloads, so parts of your workloads can be lower priority than the higher priority workloads, which are user facing, and you can tag them appropriately so that Bigtable can do an appropriate job and keep your latency low. We also talked about authorized views. You can have different teams working and developing on different parts of your schema so that you can have your denormalized data that is ready for serving be developed and curated and created by different teams at the same time in parallel. So this is just showing how you can actually restrict and slice your data. Last but not least, we're very excited to launch our distributed counters in preview. Counters are ubiquitous in our use cases, be it user engagement monitoring, metrics, sales metrics, sensor activity, fraud detection, and the list goes on. At Google, we believe a lot in making 10x improvements, and we are happy to announce the preview of our distributed counters feature, which is more than 10x performant than the previous read, modify, write transactional behavior we used to have for incrementing counters. Counters can be added to any existing table, new or old, and gives you the flexibility to use on any of your use cases in the most cost-efficient manner. Many customers have, again, significant cost benefits while getting access to all these advanced features of Bigtable, and we encourage you to reach out to us if you think Bigtable can power your business. And last, in parting thoughts, change is constant and flexibility always triumphs over everything. Bigtable can be that flexible performance store that grows with your needs. Thank you, everyone, for joining us. And thank you, Martin, for going over these very important use cases at Snapchat.